property in this video. Suppose, like we discussed in the last video, for a diamagnet, let's have a magnetic field in a given region. Here lines of force are away from each other, so this region represents weaker magnetic field, this region represents stronger magnetic field. Suppose if you keep a paramagnetic substance, this paramagnetic substance will move towards a stronger magnetic field, from weaker magnetic field to stronger magnetic field. It will move. Stronger magnetic field, it will move. This is one important property of a paramagnet. And why is it? Because this is magnetized weakly in the direction of the applied field. So paramagnetic material gets magnetized weakly in the direction of the external field. In the direction of the external field. So whereas diamagnetic materials, in the last video we discussed, diamagnetic material gets magnetized in a direction external to the opposite to the external field, when this one is magnetized in the direction of the given field, in the applied field. And why? Because the intensity of magnetization, the other reason is also the intensity of magnetization has another important property. That is, intensity of magnetization is C and B naught by absolute temperature. And we know that I is equal to chi h and C into P naught equal to mu naught into h divided by T. So that means that chi equal to C mu naught by T. Here this constant is Curie constant. So we say that susceptibility is inversely proportional to temperature. So why? Susceptibility of a paramagnet or intensity of magnetization of a paramagnet dependent on temperature, inversely proportional to temperature. So susceptibility of paramagnetic substance inversely proportional to temperature. Let me explain that. Inversely proportional to temperature. See, if you take a piece of paramagnet, individual atoms have magnetic moment. In diamagnet, individual atoms do not have magnetic moment. Here in paramagnetism, individual atoms have magnetic moment. But you see what? The overall magnetic moment of the material, we call it intensity of magnetization is magnetic moment per unit volume. For the sample, the entire material, it is 0. Even though individually atoms have magnetic moment, the overall material, it is 0. Why? Because the magnetic moments are randomly oriented due to thermal agitation. Because of this, the net magnetism is 0. But if you apply magnetic field and if you keep this material here, let us say at 2 temperatures, so temperature 1 and another temperature, so the same specimen you are keeping at temperature T2. Let us say this is at higher temperature. At the higher temperature, you will find that it is aligning. You will find that now they are randomly oriented, even in a direction this way, that way, everywhere. But here if you see, at temperature T1, when you apply magnetic field, the magnetic moments are aligned in the direction of the external field, because the field is in this direction, it is aligning, but it is weakly aligned in the direction of the external field. This is, let's say, temperature T1. But what if temperature T2 is less than T1? Less than T1 means like the temperature is reduced now. When temperature is reduced, the alignment is almost near perfect. Not exactly, but when you decrease so much, it is near perfect. So in this way, you see, this is aligned in the direction of field, but still it is random. It is aligned in the direction of field, but the randomness has reduced almost in the direction. But there will come a temperature, and if you keep this, and this aligns almost perfectly in the direction of the external field, at that point this Curie law won't work. So this law, Curie's law, won't work. So this constant is called Curie's constant. Remember that this is Curie's constant. There is a particular temperature, and at that point it is perfectly aligned. Okay, so beyond this temperature, what happens? It will not obey this Curie's law. When I mean that for temperature, let's say this temperature is T naught. So below T naught, this susceptibility is not inversely proportional to temperature because it achieved its maximum value. And here some of the paramagnetic materials, important paramagnetic materials are aluminum and sodium, calcium, copper chloride, and one more important thing is oxygen. Even oxygen is a paramagnetic substance. So because they get weakly magnetized in the direction of field, unlike diamagnets, they won't expel. Suppose previously magnetic field lines are like this. When you keep this paramagnetic substance up here, these magnetic field lines tend to move into it. Hence, it will attract more magnetic field into it. So like diamagnetic material, this is also 1:1 lakh part. For most of the materials, it is 1:1 lakh part. Okay, so a paramagnetic materials susceptibility is inversely proportional to temperature. When temperature increases, susceptibility decreases. When temperature decreases, susceptibility increases. There will come a point the magnetic individual dipole moments of the paramagnetic atoms align in the direction of the external field. In such case, beyond this temperature, that means for temperatures less than this temperature T naught, it won't obey Curie's law. So chi and mu are paramagnetic material does depend not only on the material but also the sample temperature. Okay,